Okay, hello and welcome to another video showing you a MAT question. This is MAT 2012 question 4. Um, Quite like this one actually. It wasn't out of the big questions the nastiest one for me on this paper. I thought question 2 at the end. Um, Question 5 at the end. It's normally at the end, isn't it? And this one gets harder at the end, but I preferred this one. I tend to feel stronger on the coordinate geometry ones. I don't know if that's an illusion or not, but I've always quite liked it. So yeah, let's have a look at this. We've got essentially this question is about a circle which sits in a parabola. Yeah, or a quadratic if you like. In fact, just a simple curve y equals x squared, and it's just a circle on the y-axis. And in fact, it starts off with a circle at the centre 0, 2. It's just resting on the parabola. In other words, it's tangential here as it describes it itself. Okay, so it kind of walks you through it at first, and like typical MAT questions, the start of it is often really easy. Like I think MAT is typical for that in many ways. The first 30 or 40% of the marks are often really, really straightforward, and then it escalates. Okay, so let's have a look at this. XY is a point on the parabola, so it could be here. Yeah, it's not at A or B yet. It's a point on the parabola such that x doesn't equal 0. Show that the gradient of the line joining this point to the center of the circle, which is at 0, 2, is given by that formula. So we've got to find the gradient of this line. Well, that's no problem because we know the coordinates of that. We know the coordinates of that. The gradient you always work out by doing change in y over change in x. Now, initially, you might write down something like this, therefore, y minus 2 over x minus 0. But of course, this isn't just xy. When you've got the actual curve, considering this is a curve y equals x squared, you can of course call the y coordinate x squared. We do that kind of trick, don't we, when we're differentiating from first principles? If you remember, when we do that, we do exactly the same kind of thing. Because if you've ever got, sorry, I'm just trying to do this neatly. If you've ever got a curve and you've got the equation, well, the y coordinate is related to the x coordinate using that equation, and so we can trade them for x squared. And at that point, you realize the answer just pops out straight away. Questions like that, they worry me just in terms of like, well, I can just see the answers right, and I feel like I'm not doing any working. I hope they give my diagram some justification. Maybe I'd write out change in y over change in x, but it just feels like I've done nothing for it. I've done it the right way around, haven't I? That minus that over that minus that, and I've got the same answer as them, yeah. But I do worry, have I shown enough to guarantee that the examiner doesn't just think I've looked at this and written it down? Because obviously that's not right, is it? Just make it clear you're working at a gradient. Maybe we should put, change in y over change in x, but hopefully they could see with the quality of the rest of our answer that we know what we're doing. But I don't know if that would necessarily get you the marks. It would be interesting to look at the mark scheme. I haven't really thought about it. But yeah, it would be interesting to look at the, really strict mark scheme and see, what they really wanted to show there, because it's just obviously the gradient, if you ask me. Anyway, so that's that one. Just give an indication using a diagram that you've actually found the gradient of that line. That's the way I would do it. Okay, with the help of the result in part one, or otherwise, or they're always tempting you with the or otherwise remark, show that the coordinates of B are given by, so we're dealing with B now, are given by square root of 3 over 2, 3 over 2. So, okay, we've got to find the coordinates of B, essentially. Well, what do we know about B? Well, we know the gradient of B to this point now, because the gradient for any point on that line should be that, x squared minus 2 over 2, and that applies to B as it does to every other point on the parabola if you're finding the gradient up to that from that point to the center of the circle. Now, there's another way of finding that gradient, of course, and that's to differentiate y equals x squared. That would be the gradient of the tangent. So the gradient of the normal would be minus 1 over that, the negative reciprocal. And so that should have exactly the same gradient as this. So I've got minus 1 over 2x equals x squared minus 2 over 2. And that's an equation with one unknown, so I should be able to solve it to find x, and hopefully it's going to equal the x coordinate here. So what am I going to do here? I'm going to get rid of the 2's. I'm going to times by x. Hang on a second. I feel like I'm doing something slightly off here. Oh yeah, I can see it. Can you see the mistake I've made? I do this kind of stuff all the time. Just a miscopy. Yeah, you were probably screaming at the screen when you saw it. There's an X down here, isn't there? Not a 2. Look, I've just the errors crept in up here. It's crazy, isn't it? Some of the mistakes you make, I'm always like reflecting on my mistakes, and so many of them are just crazy slip ups. It shows the importance of checking you're working, and I should probably slow down. I try and rush things, and it doesn't help. Anyway, so that x is going to cancel with that x, leaving minus a half equals x squared minus 2. Add that over, you're going to get 3 over 2 is x squared, and so x is the square root of 3 over 2. Cool. And y, all on this curve, is x squared, so y is 3 over 2. And hence we've got the coordinates of b, and this is definitely not a because I need the positive 1. And I can see that from the diagram, b is a positive 1, a is a negative 1. So I definitely need a positive 1, so b's coordinates is root 3 over 2 and 3 over 2. Done. So that one wasn't too bad either. 3 is where it gets a bit harder. Show that the area of the sector of the circle enclosed by the radius to A, the minor arc AB, so that's not the major arc where you go all the way around, it's a minor arc AB, and the radius to B, so we're talking about this little pizza slice down here, show that the area of that equals this. So I'm going to draw a little picture here. We've essentially got, like I say, a little pizza slice like that. This is the radius of the circle. And what else do we know? Well, we know B's coordinates and we know A's coordinates because it would just be the negative of B's. A's minus big root, sorry, not a little root. It's not like root 3 over 2 like in trig. Be careful. And that's 3 over 2. And this is root 3 over 2 and 3 over 2. So we've got exactly the same y coordinates. So we're trying to find the area of a sector. Immediately I'm thinking half r squared theta. That seems, natural to kind of think of. But I'm also thinking I might as well just chop this in half because it makes the trig slightly easier then. Don't have to use cosine rule then. I can just use SOHCAHTOA trig. Now, I know as that's got the coordinates 0, 2, and this is a y coordinate of 1.5, that side must be a half in length. I also know that this is going to be a distance of root 3 over 2. So that means I can actually work out r, I think, because I can just use Pythagoras and do a half squared, or I could write down r equals here, a half squared plus root 3 over 2 squared. Well, a half squared is a quarter. Square that, you get 3 over 2. So you've got a quarter plus 3 over 2, which is 6 over 4. Quarter plus 6 over 4 is 7 over 4. Don't forget to square root. So that's root 7 over 4. And so what have we got here? We've got cos theta. And the reason I'm using cos theta is because they've got something to do with cos. So, and here what I'm trying to establish here, because the formula is a half r squared theta for sector area, I'm trying to understand what theta is, and hopefully I'm going to get an inverse cos statement. Well, when I work out this, what have I got? I've got cos theta equals adjacent divided by hypotenuse. And I'm just going to square root that 4 and make it a 2, because that way I can double top and bottom and I get 1 over root 7. Look at this, at that point I thought, yeah, I've done it again. I've written 2 when I said 7. What is the matter with me? My hand does not want me to succeed. But looking at that, that looks like the right way to go about it, doesn't it? Because we get inverse cos of 1 over root 7. I've put a minus there. What is the matter with me tonight? I'm not in control of my own hands. I've lost bodily autonomy. Okay, right. Theta is inverse cos of 1 over root 7. Now, that's nice because now I can just use area is a half r squared. Now, r squared is going to be 7 over 4. Oh, look at this. Times by theta. But remember, theta is actually going to be double this because I need the whole angle. So times by 2 inverse cos of 1 over root 7. And hence, I get area equals exactly what they said I was going to get, because r is root 7 over 4. It's just 7 over 4. The half and the 2 cancel, and you're left with the answer. And I might just colour in a little square there to show that I've finished the proof. Yeah. Hopefully my diagrams are, explain to them what I'm doing as well. I've always thought that a nice clear diagram, hopefully to give you credit for it. Okay, part 4. What are we doing on part 4? What are we doing? Suppose now that a circle with centre 0a is resting on a parabola where a is greater than 0. Okay, so we're no longer at 0, 2. The circle is 0a. So they're varying the height of the circle. It's still resting on it though. where a is greater than 0. Find the range of values of a for which the circle and the parabola touch at two distinct points. Yeah, two distinct points. Because I guess it could just sit here at the bottom, touching at one repeated point, if you like a repeated root. But we're trying to find a range of values of a for which it touches at two distinct points. Now, we already know, let's do it the same way as we did last time, that, x squared minus a over x is the gradient. And, minus 1 over 2x are both the gradient of the normal, if you like, to the point of contact. Just to show you what I'm talking about there. I'm saying basically, I'm doing exactly the same thing as what I did earlier. I'm just saying, okay, call this circle 0a, and I'm just going to go through exactly the same working because I want to find out what the coordinates of b are. Basically, that would be kind of handy. I want to think about that anyway. How would I find the coordinates of b? And then I can think about what values could I not have got for a when I was finding it. So I'm going to equate this to minus 1 over 2x. I'm going to cross out the x's, and I'm going to get x squared minus a plus a half equals 0. And so obviously x was going to be the square root of a minus a half, plus or minus, I guess, really. And I looked at this and I thought, well, what values can a be? Yeah, find a range of values of a. Well, a's got to be bigger than a half. Yeah. It can't be equal to a half, actually. If it's equal to a half, you get the square root of 0. And the square root of 0 will give you one x value. But we're looking for two distinct x values, two distinct points. So actually, you do have to rule out the possibility that it's a half. Basically, if a is less than a half, it's just going to sit there snugly in the bottom of the pocket. But if a is, once you get up to here, like beyond a, the middle of the circle being a half, then suddenly the circle starts to, there's a gap at the bottom here. It's interesting that, isn't it? When when a circle kind of fits snugly in a quadratic. I think it's quite an interesting little project they're looking at here. So anyway, a is greater than a half. That's that one done. Part 5, and I think you can see now why I was thinking this one's not too bad. If you hit on the right ideas, anyway, it really isn't too bad in my opinion. Okay, let r be the radius of the circle with center 0a. That is resting on the parabola. So it's still definitely resting on the parabola. Express a as a function of r, distinguishing between the cases that arrive, distinguishing between the cases in which the circle is and is not in contact with the vertex of the parabola. Yeah, in contact with a vertex of the parabola. Always read questions really carefully. Basically, this is describing the two things which can happen. It would either be in contact with the vertex, i.e. it touches once, or it will be up higher, i.e. it touches twice. That's what's actually going on here. There's only two possibilities. It touches once down here, or it touches twice. And we just found the range of values of a for which it touches twice. And so either a is greater than a half, yeah, and this is a more complicated case really, in which case what do we have? Well, we already know x squared is equal to a minus a half. We're certain of that. And what we're interested in is expressing a as a function of r. Well, we also know that we've got the equation of the circle, which is x squared plus y minus a squared equals r squared. And we're trying to find r as a function of a, or a as a function of r, sorry. Let's get it the right way around. What we can do with this equation is we already know that x squared is a minus a half. And on this circle, well, on the parabola at least, y is x squared. So I can swap that a with a minus a half. That's probably the most difficult bit. So you get a minus a half minus a all squared. R squared I'm certainly going to leave there. And x squared, well, as I said before, that's just a minus a half. So now I can use this to express a in terms of r. These a's are going to cancel, which is lovely. This is going to become minus a half plus a quarter, which is minus a quarter. And so a is r squared plus a quarter, which is lovely. Yeah. I think the hardest thing to spot is actually how you eliminate y there, but of course y is x squared at the point that we're interested in, so yeah, because it's in the y coordinate is also on the curve as well as the circle. That's why we're okay with doing that. So we can give it exactly the same y coordinate as y coordinate of b, and the y coordinate of b is obviously a minus a half. Okay, so that was lovely. Or 0 is less than a, which is less than or equal to a half. Yeah. And what's going to happen here? Well, just by thinking, I reason that it will just be sitting there, and therefore the radius will be the the value of a. Radius will take the value of a, and therefore r equals a in this case. That's it. That is absolutely the end of the question. I didn't think it was too bad at all. I certainly think it was one of the nicer ones on this particular year. But there we go. Oh, it's shifted all down. Okay, hope you enjoyed the video. Keep up the hard work and all the best. Bye bye.